So good afternoon, everyone. So we'll begin. Um, One quick announcement is that there is a homework 3 that's available on Teams, and this deals with the material that we covered up to last week. And you can look in the Teams SharePoint, the files, class materials, homeworks, and you will find this homework 3. Okay, so the last time we were looking at errors in inverses and solutions to linear systems. A related concept that we saw was the concept of compatible norms. And compatible norms are norms such that they satisfy a submultiplicativity type property, but with a combination of a vector norm and a matrix norm. So specifically, if there is a vector norm such that AX is less than or equal to the norm of A times the vector norm of X, then this vector norm and this matrix norm are said to be compatible. Okay, so so based on this, we were looking at bounding the errors in computing solutions to linear systems of equations. We saw one formulation, and towards the end of the previous class, we saw this other formulation where we look at a perturbed system, this one here. So where the matrix A and the right hand side B are both perturbed by matrix A delta and a vector B delta multiplied by some small number epsilon. And we are interested in understanding the first order behavior of how the solution X epsilon is related to the solution X as this for very small values of epsilon. And so this is what we call the perturbed system. And we showed that if you look at the relative error in X due to perturbations, that is the norm of X epsilon minus X divided by the norm of X, that can be written as, that can be upper bounded by epsilon times the condition number of A with respect to some norm, which is actually a compatible norm with the norm used to evaluate this relative error in X. So this times the relative error in B, actually epsilon times this is the relative error in B, and epsilon times norm of A delta over A is the relative error in A, plus a term which is order of epsilon squared. So if epsilon is small enough, this term will dominate this term, and so you can drop this term. And essentially what we said is so as I mentioned, the relative error in B is epsilon times norm of B delta divided by norm of B. We'll call this rho B. And similarly, rho A is epsilon times norm of A delta over norm of A. Then we can upper bound this relative error in X as the condition number times rho A plus order of epsilon squared. So this is the punchline that to a first order approximation, the relative error in the computed solution, X of epsilon, is bounded by the condition number of A times the sum of the two relative errors. Okay, so that's where we stopped in the previous class. And again, it brings out the fact that if you have a well-conditioned matrix, K of A will be close to 1. And so the error in the solution is going to be of the same order as the error in A or B. Whereas if A is a poorly conditioned matrix, K of A will be a large number. So the error in the solution will be much larger than the error in either A or B. It's not will be, this is the bound we have on this. So again, it's possible that for specific A's and specific right hand sides B, the relative error in the solution may not be as big as this. It doesn't mean that it will always be as big as this, but this is the bound we are able to get. Okay, so let's continue. So now that concludes this chapter on norms. So now I'm
Sir,
moving.
I have a question.
Yeah.
Uh, Sir, now that we derived this thing for same epsilon for matrix A and B, that is same perturbation
Hmm.
parameter.
Hmm.
So, if the epsilon is different from for A and B, will the
Hmm.
final formula that relative error plus B plus relative error in A times condition number will hold?
So these are all just upper bounds. Okay, so if you want to perturb them by different amounts, a simple fix to this is to take epsilon to be the max of the two epsilons. And
Oh,
everything we're saying here is valid. Here we're just looking at the first order behavior, the sensitivity to small perturbations in A or B. And the punchline is again that whatever is the relative error in B plus the relative error in A, that gets amplified by this coefficient K of A.
yes.
Oops. No, do that. Okay, anyway, delete. Okay, so we'll continue. So now I come to actually chapter 1 of the Horn and Johnson textbook, which is on eigenvalues and eigenvectors. Um,
Sir,
so the yeah,
yeah, can you scroll up a little bit? Yeah, no, scroll up in the first page. Yeah, I, sir, again, somewhere you have written, sir, is this, see, is this norm or matrix norm for A, what you have written? Like,
good
yeah,
question. This should have been the matrix now. Yeah,
yeah, sorry, thanks.
the typo. This is the same matrix norm that is used here to compute the condition number of A. Okay. So now we come to, you sort of have to rewire your brain a little bit, and this is a different topic. It's eigenvalues and eigenvectors. Again, a super important topic from the point of view of matrix theory. So the fundamental equation of eigenvalues and eigenvectors is very simple. It's stated right here, Ax equals lambda x. And here A is an n cross n matrix, and x is an n by 1 vector. Lambda is a scalar. Okay, and so lambda belongs to C. And x can be any vector as long as it's not the all zero vector. Of course, the all zero vector will satisfy this equation, but we don't care about that. That's a trivial solution. So for non-zero x, if you can find a vector x and a scalar lambda such that Ax equals lambda x, we call this pair x and lambda as an eigenvalue. Okay, this is not correct. To be sort of consistent, this is an eigenvector eigenvalue pair. Okay, and the key thing, reason I underline this here is because these always occur in pairs. Okay, so you associate an eigenvalue, and associated with any eigenvalue, I mean, you cannot define an eigenvalue without saying that there is an x not equal to 0 such that Ax equals lambda x. And similarly, you can't say that x is an eigenvector without saying that for some complex valued lambda, Ax equals lambda x holds. So they're always in pairs. Okay, so just to motivate, here are two quick, simple examples where eigenvalues and eigenvectors matter. So suppose you want to find a solution to this differential equation here, du over dt equals au. Here A is some constant matrix which is independent of t, but u is a function of t and you're trying to solve for u of t. U of t is a vector, okay, and is evolving with time. And the way it evolves is such that it satisfies this differential equation du by dt equals au. Of course, in the scalar case, you've certainly seen this in your undergraduate program. If I give you this equation du by dt equals au, you will take u to down there and dt up here, and then you'll integrate both sides. You will get log u is equal to at, and from that you get u is equal to some constant times e power at, where the value of the constant depends on the initial condition, that is the value of u at t equals 0. So if somebody tells you what the value of u at t equals 0 is, you can find what this constant is, and you know that this is the solution. So if I had to use this and say what happens in the matrix case, I could potentially think about writing capital A in the exponential here. But for now, just consider u is equal to e power lambda t times x, where x is an eigenvalue of A, and sorry, lambda is an eigenvalue of A, and x is an eigenvector of A. If I make this substitution, u is equal to e power lambda t times x, if I substitute that, yeah, so how do I explain this to you? So a times u will be a times e power lambda t times x, which is equal to e power lambda t is a scalar, so I can take that out of the multiplication. So it's e power lambda t times ax, and ax is the same as lambda x because lambda and x are an eigenvalue eigenvector pair. So a times u is equal to lambda times e power lambda t times x. So basically au will be equal to lambda times u, and then if I consider du by dt, so if I differentiate this with respect to t, the only thing that depends on t is just this e power lambda t, and its derivative is lambda e power lambda t. And so du by dt is also equal to lambda times e power lambda t times x, which is equal to lambda times u. So au is lambda times u, and du by dt is also equal to lambda times u, so it satisfies this differential equation. And more generally, u can be written as a linear combination of solutions of this form corresponding to different eigenvalues and eigenvectors. Now another problem is, suppose you want to solve a constrained optimization problem, such as maximize x transpose ax subject to the constraint x transpose x equals 1, where A is a real valued matrix which is also symmetric, so A equals A transpose. Then the conventional approach is to use the method of Lagrange multipliers, where you define this Lagrangian function L, which is x transpose ax minus lambda times x transpose x. Then if we differentiate this with respect to x, now this is a vector derivative, so you'll have to take this on faith, but the simple explanation is that the way to differentiate with respect to a vector is to differentiate with respect to each of the components of the vector partially, and then stack them together as a vector. Okay, the derivative of a scalar with respect to a vector is a vector whose dimension equals the dimension of the vector, and the entries are equal to the derivatives of the scalar with respect to each of the components stacked one above the other. And if you do that for this particular Lagrangian function, it is not difficult to show that the derivative is 2 times ax minus lambda x. And so if you set the derivative equal to 0, you get this equation here, 2 times ax minus lambda x equals 0. Or in other words, ax equals lambda x, which is the eigenvalue eigenvector equation. So these are two simple examples where eigenvalues and eigenvectors arise naturally when you're trying to solve some problems. And here is an example to just visualize eigenvalues and eigenvectors. So suppose A is this simple 2 cross 2 matrix with entries 4, 1, 1, 4. If I take x1 to be this vector 1, 0, then Ax1 will be the first column of this matrix, which is 4, 1. So here I show that in red. So x1 is the vector 1, 0, and Ax1 is going along this direction. The x component is 4 and the y component is 1. And similarly, if I take x2 to be 0, 1, then Ax2 is the second column of this matrix, which is 1, 4. And that is shown in green here. Ax2 is in this. So you see that x1 and x1 and Ax1 point in different directions. x2 is like this, Ax2 is pointing in a different direction. Whereas if I choose x3 to be 1, 1, then when I do Ax3, I get 5, 5, which is 5 times this vector x3. So it points in the same direction as x3. So that is shown in black here. So similarly, if I take x4 as 1 minus 1, then Ax4 will be 3 minus 3, which is also pointing in the same direction. It is 3 times 1 minus 1. So these eigenvectors are very special vectors where when you multiply the matrix by the eigenvector, you get a vector that is pointing in the same direction as the original vector. Okay, so how do we find these eigenvalues? I guess you guys know this already, so I'll just quickly, for the sake of completeness, discuss this. So consider A to be an n cross n matrix. It could be complex also, the same thing, whatever I'm going to say holds for complex also. So if we consider the equation Ax equals lambda x, this implies that A minus lambda times the identity matrix times this vector x equals 0. And this kind of an equation where you have a matrix times a vector equals 0, this is called a homogeneous equation. The right hand side is 0. That's when it's called a homogeneous equation. Okay, so one thing is that we wanted these eigenvectors to be non-zero vectors. Of course, if I set x equals 0, this will satisfy this equation, but we don't want that solution. So if x should be non-zero, that means that this A minus lambda I must have a non-trivial null space. Or in other words, lambda is such that A minus lambda I is singular. So at this point, it should look a little magical to you. So we see lambda I is a highly structured matrix. It's just a scaled version of the identity matrix. By subtracting lambda times I from A, I'm able to arrive, no matter what A is, if I take the right scaling lambda here and do A minus lambda I, the columns of A minus lambda I should become linearly dependent. Okay, and then this matrix should become singular. So I'm looking for such kind of lambdas. And if I want this matrix to be singular, one way to test it is to find its determinant. And whenever the determinant of this matrix goes to 0, we know that this A minus lambda I is going to be rank deficient and this matrix will be singular. So the determinant gives us a test. So lambda is an eigenvalue if and only if determinant of A minus lambda I equals 0. So this is a very crucial observation, that lambda is an eigenvalue if and only if this determinant of A minus lambda I goes to 0. Obviously, if determinant of A minus lambda I is 0, then it means that the A minus lambda I is singular, and therefore you will be able to find a non-zero vector x such that A minus lambda I times x is equal to 0. Contrariwise, if lambda is indeed an eigenvalue of A, It implies from the definition that there is a non-zero x such that ax equals lambda x, or a minus lambda I times x equals 0 for some x not equal to 0, which means that the matrix A must be singular. So, and therefore its determinant must be equal to 0. So these two statements, these two points are actually an if and only if statement. Lambda is an eigenvalue of A, and determinant of A minus lambda I equals 0 are if and only if conditions. And this equation, determinant of lambda A minus lambda I equals 0, is called what?
Characteristic.
Yes. It's called the characteristic equation. It's a polynomial of degree n. Okay, that comes about if you simply expand this definition from the definition of the determinant, you will see that this will be a polynomial of degree n. And and also corresponding to any eigenvalue lambda, there will always exist at least one non-zero eigenvector by definition. Okay, they always occur in pairs. I'm repeating my point. So that's it. So this is how we find the eigenvalues. We have to set the characteristic equation or find the solutions or roots of the characteristic equation, and that gives us all the eigenvalues of the matrix. So again, for example, if I consider the matrix 4, 2, -5 and -3, then if I consider determinant of A minus lambda I equals, so let's see, determinant of, so this is my A, so let's say A minus lambda I is the determinant of 4 minus lambda minus 5, 2 and -3 minus lambda, which is equal to 4 minus lambda minus 3 minus lambda plus 10. Okay, and if I set this equal to 0, then I'll get, so you have to simplify this, so that will give you lambda minus lambda times lambda is lambda squared, and 3 lambda minus 4 lambda gives me minus lambda. Okay, and then I have minus 12 over here, but there's a plus 10, so I'm left with minus 2 equals 0. And the solutions to this are lambda equals -1 or +2. Okay. So, so if I now compute, so these are the two eigenvalues of this matrix. And if I now compute A minus lambda 1 times the identity, so let's call this lambda 1 and let's call this lambda 2. Then this times, if I take x1 to be a corresponding eigenvector, this will be equal to 5, 2, 5 minus 2 times, now this is a slight abuse of notation, I'll call this vector x1, so I'll call this x1, x2, and I set this equal to 0, and I want to solve for what x1, x2 satisfies this. It's easy to verify that x1 is the vector 1, 1. If I just take 1, 1 here, this becomes 0, this becomes 0. And similarly, if I take A minus lambda 2I times x2, that becomes this minus, so 4 minus 2 is 2, and this is 2, and this is -5, and -3 minus 2 is -5 again. This times, say, x1 dash, x2 dash, equals 0, that implies the vector x2 is equal to, I can just take it to be 5, 2. So notice that basically if I take A minus lambda 1 I, that is this matrix, the column of this is 5, 2, and that gives me x2. And similarly, if I do A minus lambda 2I, that gives me this column, and that is going to be equal to x1. Okay, so just maybe just for I'll just indicate it like this. So this is something that is an interesting observation, that the columns of A minus lambda 2I actually give you x1, the eigenvector corresponding to the first eigenvalue, and vice versa. So this only works for 2 by 2 matrices. It doesn't work for larger dimensional matrices, but nonetheless it's an interesting observation. Um, So basically, when I multiply A with a vector x, most vectors will not satisfy Ax equals lambda x. Only special numbers are um, eigenvalues, and special vectors are eigenvectors. Normally, if I take Ax, it will scale the different components of x by different amounts, and it will rotate the vector x, and so it won't point in the same direction. The ones that point in the same direction are called eigenvectors, and there is a corresponding scaling factor which is denoted by, or which is defined to be, the eigenvalue. Okay, so this is the basic notion of eigenvalue and eigenvectors and how to find eigenvalues. And once you found the eigenvalues, you compute A minus lambda I for each eigenvalue, and you find one vector in the non-trivial null space of A minus lambda I, and that gives you an eigen, or rather you find a basis for the span of the null space of this matrix, and that gives you the eigenvectors corresponding to that eigenvalue. So now there's
Sir,
a couple of more definitions. Yes.
there is not any restriction on A, right? I mean, A only should be a square matrix. It can be singular as well. Still, eigenvalue and eigenvector will exist.
Yes. So basically, if A is singular, then there is an x which is non-zero such that Ax equals 0. But of course, I can write 0 as 0 times x. So then it satisfies Ax equals lambda x, where lambda equals 0. So if A is singular, then certainly you can say that lambda equal to 0 is one of the eigenvalues.
Yeah, yes, sir.
So the spectrum of a matrix, sigma of A, is the set of eigenvalues of A. And again, the spectral radius rho of A is the largest magnitude eigenvalue, which is equal to max of mod lambda, where lambda belongs to sigma of A. So this is just writing the spectral radius in terms of sigma of A. Another small point to note is that if Ax equals lambda x, then A times Cx is equal to lambda times Cx for any 0 not equal to C belonging to some complex space. And so basically, if x is an eigenvector, so is Cx for any C not equal to 0. Okay. So now the other thing is, which will sort of lead us to the characteristic polynomial and studying it, is that um, given any polynomial, So let's say P of t, ak t power k plus a k minus 1 t power k minus 1 plus a0. This is a polynomial in t, and a in c to the n cross n. Okay, so we can define p of a. This is the polynomial evaluated at a matrix valued point a. So we'll define it as ak times a power k plus a k minus 1 a power k minus 1 plus a0 identity matrix. Otherwise you can't add it to these terms. So this is how we define the polynomial evaluated at a matrix. Now this P of A, it will always have the same eigenvectors as the matrix A itself, and the polynomials, the eigenvalues of P of A. P of A is an n cross n matrix because this is n cross n, this is n cross n, this is n cross n. When you add up all these terms, you will get an n cross n matrix. And its eigenvalues are closely related to the eigenvalues of A itself. And so that is the following theorem. Yes?
The screen not updated so far.
Can somebody else confirm?
It is getting updated for me, sir.
Proper.
Yeah, maybe, if it just wait for a second, if it doesn't update, then just drop off and join again. You should see the new screen. The polynomial. Okay, and if lambda is an eigenvalue a and x is a corresponding eigenvector, then P of lambda is an eigenvalue of P of A and x is an eigenvector of P of A associated with the eigenvalue P of lambda. Okay, so how do we show this? This is very simple. So if I take P of A times x, this is going to be equal to ak a power k x plus a k minus 1 a power k minus 1 x plus etc. plus a0 times the identity times x, which is equal to x. Now, of course, a power j times x is equal to a power j minus 1 times ax, which is equal to lambda a power j minus 1 times x. And so we can keep going like this, go to j minus 2 and so on. And so this is going to be equal to lambda power j times x. Okay. So that means that P of A times x is equal to, So it becomes lambda power k times x here and lambda power k minus 1 times x here and so on. So it becomes ak lambda power k x plus ak minus 1 lambda power k minus 1 x plus etc. plus a0 times x, and x is multiplying all these terms, so I can pull it out and write this as ak lambda power k plus ak minus 1 lambda power k minus 1 plus etc. plus a0 times x, and this is nothing but p of lambda. This polynomial evaluated at the number lambda times x. So we see that p of a times x equals p of lambda times x. This is an n cross n matrix. This times x equals, this is a scalar. So p of lambda times x, which means that p of lambda is an eigenvalue of a and the corresponding eigenvector is x. P of lambda is an eigenvalue of p of a and the corresponding eigenvector is x. So based on this, so for example, if sigma of a were the two values, say -1 and 2, then what is sigma of a square? A is a 2 cross 2 matrix. It has two eigenvalues, -1 and 2. So sigma of a squared will be lambda 1 squared and lambda 2 squared, which is equal to 1 and 4. And as I already mentioned to you earlier, A is singular if and only if 0 is part of sigma of A. Because if A is singular, if and only if ax equals 0 for some non-zero x, which is true if and only if lambda equal to 0 is an eigenvalue.
Sir,
Yes,
so in the above example, the polynomial is px equals x square, right?
correct.
Okay, thank you.
Okay, so now let's discuss this characteristic polynomial in some more detail. So this basically we answer questions about the eigenvalues of A, and for example, how many eigenvalues does an n cross n matrix have, and when will it have n linearly independent eigenvectors. Okay, so those are the type of questions we want to answer. So the characteristic polynomial, will define it in a slightly different way from what I said earlier. It's just a change of sign. We'll define it to be PA of t, which is equal to determinant of ti minus a. Okay, this is a polynomial of degree n, and its roots are the eigenvectors, eigenvalues. So why is this a polynomial of degree n? It's because if I think of it, I mean, just write it for the 2 cross 2 case so that you see what happens. This matrix will look like t minus a11 minus a12 minus a21 and t minus a22. And if I take this determinant, it will be equal to t minus a11, t minus a22 minus a21, a12. And so you can see that this is a quadratic polynomial. So in the n cross n case, by similarly writing it out, you will see that it has to be a polynomial of degree n. The coefficient of t is always 1. So when I take the determinant of this, I cannot suddenly get a polynomial whose degree is n minus 1. It will always be of degree n. So there is what is known as the fundamental theorem of algebra. We will not prove this here, we'll take it on faith, but it says that any polynomial of degree n and complex coefficients or with complex coefficients has exactly n zeros counting multiplicities. Okay, so multiplicity just simply means how many times a particular lambda occurs as a zero of PA of lambda. So if you count multiplicities, then there are exactly n eigenvalues. So for example, the n cross n identity matrix has exactly n eigenvalues, all are equal to 1. Now, because, yes,
Sir, complex coefficients means real also is included.
yes.
Okay.
Now, suppose we let lambda 1 through lambda n be the eigenvalues of A, where repeated eigenvalues are okay, they're just counted as lambda 1, lambda 2 up to n. So let lambda 1, lambda n be the eigenvalues of A, counting multiplicities. The n eigenvalues of A counting multiplicities. Then these are the zeros of the characteristic polynomial. So we can write PA of t equals t minus lambda 1, t minus lambda 2, t minus lambda n. Okay, so this is a factorized form of the characteristic polynomial, and this polynomial is identical to this determinant of ti minus a. So in particular, if I look at the coefficient of t to the n minus 1 in this polynomial, that's just the sum of the eigenvalues. And similarly, if I look at the coefficient of t power 1 here, you can see that it's just going to be t power 1 will be minus a11 minus a22. And the coefficient of t power n minus 1 here will be minus of lambda 1 plus lambda 2 plus etc. up to lambda n. So those two coefficients must match if the polynomials are, if we say two polynomials are equal, it means that the coefficients of t power n minus 1, all the way down to t power 0 must match. T power n obviously matches because the coefficient of t squared is 1, and here also when I take the coefficient of t squared in the in the lambda 1 lambda 2 case, that will also be equal to 1. But basically, if I look at what happens to the coefficient of t to the n minus 1 here, it's going to be equal to a11 plus a22, which is the coefficient, which is equal to, which must equal lambda 1 plus lambda 2, which is the coefficient of t to the n minus 1 here. So basically and similarly, if I take the constant term here, that's the product of these eigenvalues, and the constant here is going to be, all I have to do is the constant term will be obtained by setting t equal to 0 in this PA of t, and so the constant term is just nothing but the determinant of the matrix A. So the product of the eigenvalues equals the and the sum of the eigenvalues equals the trace of the matrix. So that's the following theorem. If lambda 1 through lambda n are the eigenvalues of A, so the determinant of A is the product of the eigenvalues, and the trace of A is the sum of the eigenvalues. So just to maybe make it clear, if you look at if I set t equals 0 here, what I get is minus lambda 1 into minus lambda 2 up to minus lambda n, which is minus 1 power n times the product of the eigenvalues. If I set t equals 0 here, I will get determinant of minus A, which is again going to be equal to minus 1 power n times determinant of A. Those two must be equal, and therefore minus 1 power n cancels with minus 1 power n, and what you're left with is determinant of A is the product of the eigenvalues. And similarly, if I look at the coefficient of t power n minus 1 here, it's going to be minus lambda 1 minus lambda 2 up to minus lambda n. And here, if I look at the coefficient of t power n, t power 1, I have a11 plus minus of a11 plus a22, which is nothing but the negative trace of the matrix. So negative trace of the matrix is the same as the negative sum of the eigenvalues, and so we have this part here. So for the sake of completeness, I'll just say here coefficient of t to the n minus 1, and this is obtained by looking at the coefficient of t power 0. Or the constant term. Or the other way is set t equals 0 in okay, so there are a couple of other results. Before that, maybe I'll just write this one thing out, which is what is the procedure to find eigenvalues and eigenvectors? Two-step procedure. First step is solve the characteristic polynomial to find lambda I. Now this can be done only in closed form only for the 2 cross 2 case. For larger dimensional cases, you'll have to solve it by hand for specific A matrices, or you'll have to use a solver, a zero finding algorithm to find all the zeros of that polynomial equation. And 2, find eigenvectors by finding the null space of A minus lambda I. Of course, this is okay for small dimensional systems, but if you have a very large dimensional system, then the errors can accumulate. So this is not the most desirable way to compute eigenvalues and eigenvectors for very large dimensional systems. We'll see that much later, some numerical techniques to find eigenvalues and eigenvectors. Now, some couple of properties of these eigenvectors, but maybe before that, I just want to mention about multiplicity. So in this context, we consider multiplicity to be simply the number of times it occurs as a zero of this polynomial. But a more thorough way of looking at multiplicity is in terms of the derivatives of a polynomial and whether this particular eigenvalue is a zero of the derivative of the characteristic polynomial. So specifically, a polynomial P of t has lambda as a zero of multiplicity k which is always greater than or equal to 1 if and only if we can write P of t equal to, in this form, P of t to be in the form t minus lambda power k times q of t, where q of t is a polynomial such that q of lambda is not equal to 0. So basically, if I take, for example, p dash of t, dp of t by dt, this will be equal to k times t minus k power t minus lambda power k minus 1 times q of t plus t minus lambda power k times q dash of t, right? And so from this representation, you can see clearly that p dash of lambda will be equal to 0 if and only if k is strictly more than 1. For if k equals 1, then k minus 1 becomes 0, and this term becomes k times q of lambda. And of course, this term will go to 0, but that doesn't matter. Q of lambda is not equal to 0, and k is 1. So the derivative will be non-zero if k equals 1. So basically, for p dash of lambda to be equal to 0, we need that in this representation, k should be greater than 1. And similarly, if you take the second derivative, so if k greater than 1, p double dash of t, second derivative will be k times k minus 1 times t minus lambda power k minus 2 q of t plus some other terms, which will all have something like t minus lambda power m for m greater than or equal to k minus 1. Okay, these type of terms. And now once again, if so basically once again you can see that p double dash of lambda will be equal to 0 if and only if k is greater than 2. Because if k equals 2, then this term becomes t minus lambda power 0. And then if you substitute t equals lambda, this will remain equal to 1, and k into k minus 1 is going to be non-zero, and q of lambda is non-zero. So this whole thing will be non-zero, even though these terms are going to 0. And so p double dash of lambda will be 0 if and only if k is greater than 2, and so on. So basically this calculation shows that P of t, rather, so lambda is 0 of P of t with multiplicity k if and only if P of lambda equals P dash of lambda equals etc. up to P k minus 1th derivative of lambda equals 0 and Pk of lambda is not equal to 0. So this is how you get a more precise definition of the multiplicity of eigenvalues. Okay. So just a couple of properties of eigenvectors. The first property is that if lambda 1 through lambda n are distinct, that is, no two of them are identical, then there exists a linearly independent set of eigenvectors. Okay, so this is saying a little more than, so if I have lambda 1 to lambda n being distinct eigenvalues, corresponding to each eigenvalue, I will have one eigenvector that comes from the definition itself, one non-zero eigenvector. But what we are saying here is that these eigenvectors are going to be linearly independent, which means that these eigenvectors will have unique directions. And since they are sitting in the n-dimensional space, they will actually span R to the n. The second property is that if there are repeated eigenvalues, then A will have n linearly independent. I'm going to use more short forms, linearly independent eigenvectors, provided rank of A minus lambda I equals n minus r. Okay, and this should hold for every distinct eigenvalue. Okay, so this is sort of answering the question we asked at the beginning of the class, that is, when will the matrix A have n linearly independent eigenvectors? One case is when all the eigenvalues are distinct. Another case is when if there are repeated eigenvalues, but for each eigenvalue, if you compute the rank of A minus lambda I, and that is equal to n minus r, where r is the number of times this eigenvalue is repeated, then also it will have n linearly independent eigenvectors. However, the directions of the r eigenvectors associated with these repeated eigenvalues are not unique. There are multiple ways in which you can find a basis for that r-dimensional space, and therefore multiple ways in which you can find a set of n linearly independent eigenvectors. And the third point is that if v1, v2 up to vr are eigenvectors, associated with are repeated eigenvalues which are all equals, they're repeated, so we call them lambda. Then any v belonging to span of v1 through vr is also an eigenvector of eigenvector associated with the same eigenvalue. Okay, so for example, if I consider the matrix 1 0 0 0 0 0 0 0 0, then any v in span of E2 E3, okay, E2 is 0 1 0 and E3 is 0 0 1, is an eigenvector corresponding to lambda equals 0. Okay, and the identity matrix has n repeated eigenvalues all equal to 1, and so any v in R to the n is actually an eigenvector. Okay, so I'm out of time, so we'll stop here and continue again on Friday. So we'll continue discussing this. This is a long chapter, and so it will take many classes for us to get through this material. So talk to you again on Friday.